All right. So this is, I forget what week this is, but it's probably 8 or 9. I think it's actually week 9 now. But this YouTube video refers to the homework assignment that we did at the end of week 8 before going on spring break. And so that was the first time that we got to do an assignment on stand specifically. And so it's a little bit involved. So we'll just kind of go through this whole answer key pretty carefully to make sure everybody is on the same page with all that. So the first is the question about the Tobit model. And you can get the zip file if you're in a place where you can access the internet from Courseworks that has all of this. So everybody had a different state to analyze. But in each state, they're doing a model of wages, and each state top codes the top 1% or 0.1%, something like that, where for confidentiality reasons. And so in this state, which I think showing Idaho right now, there are 84 people who were top coded. They had the maximum value, and 7,133 who were not top coded. So we want to do a model for these data, and one model that may be appropriate is the Tobit model. And so that is basically a model for wages or log wages, however you want to do it, that essentially is going to treat the unknown values for the top coded as additional unknowns that we need to draw from the posterior distribution of. And all we know about those unknowns is that they're greater than some threshold A. And so you could specify any model that you want. And this is the one I chose. There's a MCMC Tobit function in MCMC pack, which is essentially as easy to use as the LM function. The only additional thing you need to specify are the censoring points. And so none of these observations are censored from below. Some of them, 84 of them, are censored from above at the value A. And we're not going to be worried about other forms. This is essentially a missing data problem for the people who are top coded. We're not going to worry about other forms of missing data in this problem. We will, starting in a couple weeks, probably consider missing data more generally. So you would want to consider whether, some people who are not working or et cetera at the lower end of the wage distribution could maybe do something to take those people into account. But for this, we'll focus on the more simple case of top coding from above. And so once you execute that line, it will draw from the Tobit model that we talked about before spring break and is talked about in Lancaster. It's essentially doing a data augmentation approach like we did for a Probit model. A Probit model is even more extreme in the sense that the latent variable in a Probit model is either positive if the person answers 1 and is negative if the person answers 0. In this case, we actually observe the value of log wages for over 7,000 people in this state, but for a small number of people, it's unobserved or only observed relative to a threshold. And so the next part B, we want to draw from the posterior predictive distribution of wages. And so remembering the distinction between a posterior distribution and a posterior predictive distribution. A posterior distribution is a distribution over the unknown parameters. In this case, it would be the coefficients beta and the standard deviation of the errors, sigma, and a posterior predictive distribution. So a posterior distribution is a distribution over unobservables, beta and sigma, that we'll never be completely sure of. But the posterior predictive distribution is a distribution for observable outcomes that is implied by a posterior distribution over the unknowns and a choice of the likelihood function. So that although it's related to the posterior distribution, it can be, or it has a number of differences as well. The posterior distribution will generally be a distribution of at least k parameters. So you have to estimate one coefficient for each predictor, and then there's one more for the error standard deviation. A posterior predictive distribution is often going to be univariate. We're only modeling one outcome here. So posterior predictive distribution, multivariate, posterior predictive distribution, oftentimes univariate. Also, the posterior predictive distribution is generally going to be a continuous distribution over unknown coefficients and error standard deviations and things like that. Whereas, not in this particular case, but often the posterior predictive distribution will often have a discrete sample space. So if the likelihood is for some discrete outcome variable like binary or count or something like that, then the posterior predictive distribution will be on that same sample space, even though it's implied by a continuous posterior distribution. So in order to do that from R, we first create a matrix of the draws from the posterior distribution. So this, well, they come out in the order. Let me just show you the column names of this. Can you see that? Sure. The coefficients for the various predictors, I made a bunch of interaction terms between gender and age and schooling and all sorts of other things. And then the 25th one in my case is the error variance. So I want to pull that last one out separately. Should be called sigma squared really, because that's what it comes out as from MCMC Pack. Then the remaining columns are going to be my draws from the posterior distribution of the coefficients. So I have 100 draws from each of the 24 coefficients that I'm interested in. I'll recreate my X matrix from this model. So that is going to be something like 7,000 observations on people, 24 predictors. I think I have to get rid of some columns that don't have any variation, or maybe not for this state. Well, that line isn't actually necessary for this state, but it might be necessary for some states if there's some predictors that don't have any variation in them. And so now what we need to do is, since this is actually sigma squared, we want to apply the following function to each row of the X matrix. So we have like 7,000 rows of the X matrix. We want to draw from a normal distribution. For each person, we want to draw 100 draws from the posterior predictive distribution for that person. The mean values for those draws will be the 100 by 1 column vector beta times X. So if X is equal little x, let's say it's going to be the first row of X. So that's this guy. And then beta is 100 by 24. X is 24 by 1. If we multiply beta by some row of X, we'll get a 100 by 1 vector to use as the column of mean values when drawing from this normal distribution. And we want to use the standard deviation, not the variance, 100 draws from the posterior variance. We're going to take the square root of those and pass those to the normal distribution. So we get 100 draws for each person from this distribution. So that is a distribution for what we predict log wages to be for a person whose covariate vector is X. But when doing these exercises, we always want to go back into the original units of the outcome variable, which were wages rather than log wages. So we want to just take those 100 draws from the posterior predictive distribution of log wages and anti-log them, so they're now 100 draws from the posterior distribution of wages. And so we'll just apply that function to every row of X, all 7,000 of them, and that will take not that long. And then we can do anything we want with that distribution of posterior predictive distribution of wages to describe it. So we can take the mean, we can take the standard deviation, we could, make a plot of it. Make a good plot of it. Try to make a good plot of it. Plotting is not working on the fly. Plot density. Whatever. You can make a plot if you want. You can't even see my plot up here, but I was fumbling around with it. So let's just pretend that never happened. We could describe the quantiles, anything we want with the posterior predictive distribution. And so the posterior predictive distribution is something in general you need to be generating. We've focused so far on relatively simple linear models and how to estimate them with Bayesian techniques because, those are the models that people are already the most familiar with. But, the only case where you can just say, my quantity of interest is a coefficient is the linear model with normal errors. And, if you had some treatment variable, then you could say, okay, this is the coefficient I'm interested in. But that's really just a special case where the sort of where part of the posterior distribution is going to be the same as a difference of two posterior predictive distributions. And so if you do a plain linear model, and let's say you have a binary treatment variable and some control variables just for simplicity, then if you drew from that posterior predictive distribution, setting the X vector equal to 1, and then take some posterior draws from the posterior predictive distribution, and then change the X vector so it's the same, except you've changed the treatment and control so it's now 0, draw from that posterior predictive distribution. If you took the difference of those two things, it would have the same distribution as the posterior distribution on that treatment variable. So that's really the only case where you can get away with not explicitly drawing from the posterior predictive distribution, but that's just because the posterior predictive distribution you want to draw from happens to be one of the margins of a posterior distribution. In general, in order to make some sort of substantive conclusions on the basis of a MCMC output, you're going to need to be drawing from the posterior predictive distribution. So we talked a couple times, I think, about the example of whether smoking causes low birth weight incidence. That's an example of a binary outcome. And so in order to get the probability, posterior probability of whether the baby will have low birth weight, given that the mother smokes during pregnancy, you have to draw from the posterior predictive distribution. So then you'll get, values on the latent variable scale. You'll have to apply those to some link function to transform them into a posterior predictive distribution of probabilities conditional on that X, and then, you know, keep the X vector the same, change smoking to not smoking, draw from the posterior predictive distribution of utility, apply the link function to the latent variable. Now you have another posterior predictive distribution for the probability of having a low birth weight kid, and then subtracting those two probabilities or whatever will give you what you estimate the change in probability to be as a result of smoking and whatnot. So really, the posterior predictive distribution is where all your substantive conclusions happen. And you always want to be framing your substantive conclusions in terms of observable variables, not saying, you know, the elasticity of something with respect to something is something else, but rather put it in terms that even not only non-Bayesians, but you know, statistically minded people can understand. Or, you know, saying like, out of 1,000 babies that are born to mothers who smoke during pregnancy, we expect, you know, 200 of them to be low birth weight, but for equivalent people who don't smoke during pregnancy, we only expect 150 of them to be low birth weight. And everybody can sort of wrap their head around that sort of a conclusion. And so, you know, drawing from the posterior distribution is not the last step. It's really an intermediate step, because you have to diagnose convergence and do, you know, other sorts of checks, and also draw from the posterior predictive distribution. So you can draw from posterior predictive distributions either using R code, or you can use the generated quantities block of a STAN program to draw from the posterior predictive distribution, and then it'll just come out with the rest of the posterior distribution that STAN computes. And so any questions about the idea of a posterior predictive distribution or what it's necessary for? It's what you believe the outcome to be given your beliefs about the unknowns. And so that's really the essence of why you were modeling this phenomenon in the first place. So in this example, you wanted to know what, you know, something about the distribution of wages in this state, but the data you have are not really suitable for that because they're top coded. And so anything that's sensitive to the tail of the distribution, like the mean or the standard deviation or various measures of inequality, is not something that is directly observable from those data. You need to have a model for the data generating process of wages in order to say something about the whole distribution, not just the piece of the distribution that you observe. And so, you know, you specified a normal model for the log wages, and you put in your predictors, and you drew from the posterior distribution, all to imply a distribution for wages as a whole. And so the posterior predictive distribution is really something that you want to get to. Yes.
So is the posterior predictive distribution, does that have 700,000?
So let's see. Yes. And you can draw from the posterior predictive distribution at any X vector you want. So you could create an X vector that's not even in your data. You know, there might be some people that exist in the population that you don't have data on, and you want to extrapolate what you think, you know, those people. So you can choose any X values you want and get a posterior predictive distribution conditional on that X. In this case, because it was census data and we wanted to ostensibly make a conclusion about the state as a whole, it was good for us to do that, to not think of, you know, a particular person, but also to take into account the distribution of X's in that state. So we have a representative sample ostensibly of, you know, 7,200 people from Idaho or whatever state you had. So we want to say something about a state distribution rather than an individual. It's good to take the posterior predictive distribution over all of those people and then, you know, do some aggregate function at the end, like the mean or the standard deviation or the Gini coefficient, something like that, on the posterior predictive distribution. But, you know, it can be done in other ways. It's always just conditional on whatever X you are interested in making conclusions about. But another thing that you'll see and can be useful, you know, if you have a survey or some sort of data set that's not really representative of the population that you're interested in making inferences about, but, you know, it was easier to get that data. So it might have been an online survey rather than, you know, a real rigorous probability sample. So you have some posterior distribution that you estimated, let's say on the online survey, and you want to make conclusions about the United States as a whole. If the, you know, variables that were in the survey are a subset of the variables that are available in the census, and that usually is the case because the census is like has the most information of anything that we have. You could, you know, download the census data on age and race and sex and, you know, those things, and take your parameters that you drew conditional on some sample that's not the sample to which you want to make or to use to make inferences about a broader population, draw from the posterior predictive distribution for the population of interest, and then make conclusions about that. So you can choose any X vectors that you want, and you can average over whatever you want. But if you wanted to make posterior predictive distribution about a particular person, like you want to put yourself in here and, you know, predict what your log wages or really what your wages would be if you weren't a student, you could get a posterior predictive distribution of Hannah. So anything.
Do you prefer to use outputs to generate the posterior distribution using the generated outputs?
You can do either way. If you're more comfortable with our code, that's certainly fine. As long as your likelihood didn't involve functions that are only available in Stan. So I think that would be the main thing. Did you have to use some function that's only available in Stan to calculate it, in which case you would have to use generated quantities. But the Stan works not just with the R interface, but Python and MATLAB and Julia and even just a shell. So the generated quantities block was more necessary in those cases because they didn't necessarily have as thorough a computing environment on the outside to do all this stuff from. So it needed to have a generated quantities block for them. Similarly with data and transformed data, you know, if you are more comfortable generating everything in R and then passing that as data, fine. If you needed to use some customized Stan function, then you could call that function in a transformed data block in order to make the data into, you know, some other form that you needed. So it doesn't really matter, just whatever is the most convenient. I would say all other things equal, it's good to do it in the Stan code. That way, if you put it up on the internet or whatever, somebody only has to take that Stan file and everything is there except for, you know, the data. So someone who might be interested in your work but not know how to use R or read R code or whatever, if they can read Stan code, then they could follow along with what you're doing. Ready? So part C, we wanted to do the same model, but using Stan. And in that case, so it's easier to see if I switch over to compiled. We had that theorem from chapter 3 of Lancaster that said the sum of squared residuals, if for some proposal for beta, is going to be equal to the sum of squared residuals for least squares. That sort of sets a floor for that. And then there's an additional piece to the residuals that comes from how far your proposal from beta deviates from the least squares vector. And that's going to be multiplied on the left and the right by the matrix in the middle, X transpose X. And so the least squares estimates and the sum of squared residuals implied by the least squares estimates can be calculated once before Stan even starts. And that can be used like sufficient statistics in order to make a Stan model that runs relatively quickly. And so I chose a small state for this demonstration because I didn't want to have R running forever. But, you know, some people had states like California and New York and Texas that had 100,000 people in the data set. And remember that although Stan is keeping track of all the derivatives for you, and so it can do its leapfrogging approximation to the Hamiltonians and all that, it's not free in the sense that just because you don't have to keep track of all the derivatives, Stan has to keep track of all the derivatives. And so if you have 100,000 observations and 15 predictors, then there's going to be 100,000 times 15 terms in the chain rule that Stan has to keep track of in order to get the derivative of the log posterior distribution with respect to, you know, each of those coefficients. And so that is going to be heavily influenced by n if we were to do this the more conventional way, where we could just write a line like y tilde x times beta comma sigma. But if we use this form here that's implied by the theorem in Lancaster, then we just have this fixed constant, the sum of squared residuals for OLS. And then what changes in each iteration is just this part here. But X transpose X is only going to be a K by K matrix. And so if K is like 15 or 20 or whatever, any sort of single digit number, double digit number, then that's not a whole lot of derivatives that Stan has to keep track of when you're multiplying a K by 1 vector by a K by K matrix by a K by 1 vector to get, you know, the scalar and then add it on to the constant to get the contribution to the log likelihood. So in this form, the number of derivatives to keep track of is on the order of K choose 2 rather than on the order of n. So for a situation like this, it's much more efficient to use this form. And indeed, if you use that form, you could, you know, do the whole, all 50 states of the, that there are data on all at once, and it would still only be involving K by K matrix in the middle there. So this was, we talked about this trick when we were first learning Stan, it has a function in OLS LP that I wrote to enable to do this. And so in order to move forward with this, the easiest way to do it is to stratify the data according to whether the person was top coded or not top coded. And so you can get the X corresponding to the not top coded people and the X corresponding to the top coded people, etc. And then for the people whose log wage value is observed, you can create X transpose X to use as part of the Lancaster trick. For the people whose Y is top coded, in that case, we're going to have to use the regular techniques in Stan. So we'll make the OLS coefficient vector X transpose X times X transpose Y. There's an inverse in there. And then the sum of squared residuals, we take our OLS coefficient vector, multiply it by X, and then subtract that from Y, take the sum of squares, and then we have the two inputs that we need for that model, which I will show, what's it, Tobit? Here. So here in the functions block, we have the function that I just referred to in order to calculate the likelihood. It takes in a coefficient vector beta, the least squares coefficient vector B, X transpose X as its middle matrix, the sum of squared residuals implied by the OLS estimates, the standard deviation of the errors that you're estimating, your original sample size, and a not important constant that has to do with the half times or the logarithm of 2 pi raised to the power of n over 2, which is just going to be a constant that we actually don't really need to even worry about. And so I define this user-defined function in Stan, and then I can call it in my model block. And so the rest of this is a little bit, well, it's fairly conventional. So in the data block, we're going to pass in the threshold for top coding, A. I'm going to pass in an array of 2 integers. So N, the first element of this is going to be the number of people who are not top coded, and the second is going to be the number of people who are top coded. This is an example of using integer array. Both of those are going to have a lower bound of 1. Similarly for K, the number of predictors we have. Then I'm going to pass in the middle matrix that I created in R, X transpose X. I'll have another vector or matrix, X, for people who are top coded. That's going to be rows equal to the second element of N. Also have K columns. We have our least squares coefficient vector and our least squares sum of squared residuals. Just to illustrate how to use the transform data block, I calculated that constant. If we only have to calculate it once, I might as well pass it into my function. It doesn't really hurt anything, but it doesn't affect any of the draws or whether any of the draws are accepted. So in my parameters block, we're going to have a vector of coefficients beta, a standard deviation of the errors sigma, and we're also going to create a vector of length n2, the number of people whose outcome was top coded, and we'll call that, y underscore a. And the very important point of this is this vector is declared with a lower bound of a. So all the values that Stan is going to propose for this vector, each of the element will have, it'll be at least as big as the threshold in log terms. So we have unknown coefficients, unknown standard deviation of the errors, and what makes this different from a regular regression model, we have also unknown outcomes. You can think about it. So there's sort of two ways to think about this. One is that the observed outcomes and YA, if you sort of glued them together, those would constitute what you might think of and has been called the complete data likelihood. So if you observed the true value for these log wages of these people, then we would just put everything together and call it the likelihood. So you can think of the untruncated outcomes and YA is constituting the complete data likelihood, or you can say I have a prior for what YA is, and it's going to be a truncated normal distribution, and the parameters of that normal distribution are based on the coefficients and the error standard deviation that I think pertains to everybody. So in the model block, it's relatively simple. There's a likelihood contribution using the function that we defined above. We have a normal prior, or you can think about this as the other part of the complete data likelihood distribution for YA. And I could put priors and probably should put priors on beta and sigma also, but it really isn't too necessary in this case, mostly because not that many observations are top-coded. So this is only slightly differing from a usual regression problem. So if we go back to that, I can set that up and then create a list of data to pass to Stan. So this needs to be a named list where the names are the same as the names that are declared in the data block of the Stan file. Then you can just call it, passing that list to the data argument of Stan. In this case, just one chain, but in general, we would do, more chains. So any questions about how you could do a Tobit model like that with Stan? No? Yeah, so it's not slight, but only a variation on a usual linear regression problem, taking into account there are some data that you only know a lower bound for the outcome. All right, so question 2 pertains to the multinomial Probit model. So this was an example where we wanted to predict whether which way of fishing people prefer to do as a function of their income. I think this is monthly income. And so if you're interested in fishing, this might be the model for you. But really, this is just sort of an example of what's known as a multinomial Probit model, which is like a Probit model that you're probably familiar with, but instead of just having 2 alternatives, you would have more than 2 alternatives. So in this case, we have 4 ways to fish, and people can choose any one of, or exactly one of those. And so this is the sort of data that we observe, although we would typically have more covariates, et cetera. And so basically, we talked a little bit about this model a few weeks ago, but that was before spring break, and maybe you don't remember about it as much. But it is a model where you have this sort of latent utility for each possible choice in the choice set. So, how much you like fishing from a boat, how much you like fishing on a beach, etc. And then the model is assuming that your expressed preference will be the one that maximizes your utility, taking into account the cost of fishing can be, different in these situations. And depending on how much income you have, you might be sensitive to costs in different ways. So there's a function already, there's a R package called MNP that you can use to draw from this model, which I will do now. So it is going to treat the first choice here, beach, as the reference category, and then model how model how your utility deviates from the reference category as a function of these predictors. Now, there's actually more than one Gibbs sampler for a problem like this. There's 3 that I know of. 2 are already available in R packages. So there was another, the Bayesian R package also had a function called RMNP Gibbs to draw from the same model, essentially. There's some additional post-processing that had to go along with it. But you have, 2 ways of estimating the same model, and then you can do a comparison to see which one is sampling most efficiently from that model. And so the second one takes a little while to do, so I'm not going to run it live, but we can look at the diagnostics that we're familiar with in order to, say which of one of these is doing better than the other. And so if we look on page 5 of the PDF, we can see the dependence plot that I like to do for the first approach, MNP. And in this case, we can see that it's not doing particularly well. So at a lag length of 1, which corresponds to the red line, we essentially have almost perfect dependence among consecutive draws. It's not quite at 1, but it's extremely close to 1. So that is basically telling you that almost all the information that you have on what the draw is going to be next is contained by the information on where the draw is now. And it's only getting a little bit of unique information for each individual draw. But sometimes the dependence is high. That's a function of the posterior, the parameterization, the data, the algorithm you use, etc. But we're sort of guaranteed that eventually the dependence is going to die down, where eventually I mean among draws that are spaced out by a large number of lags. And so we can see how the dependence declines for bigger lag lengths. The green corresponds to 8 and blue corresponds to 27, light blue 64, etc. And we can see even if we go out 350 lags, we can't get this to a situation where the gray line here gets close to 0 and stays close to 0. So, it stays maybe close to 0 for 500 iterations, and then it takes off up again, up to, dependence around 0.5, and then it comes down again, shoots up again later, doesn't achieve what we like to see and what we, saw in some simpler models, particularly with Stan, where, the lines sort of, get down, around 0 and then stay near 0 throughout the whole post warm-up period. So if we ran this for a longer number of iterations, maybe it would get to that place. But certainly through 2500, we're not seeing it settle down even for 350 lags. And so there's no thin interval that we could choose where we could test the null hypothesis that all the chains have the same distribution. So that's not exactly to say that they don't have the same distribution. It's just to say we can't really test it using what I consider to be the preferred diagnostic of not convergence. And so this is certainly a very different picture than the pictures we saw when we were first learning this plot from like a binary Probit model that basically just has like the red line would be about 0.2 and then the next line would be, you know, really close to 0. But if we look at the other approach for Gibbs sampling for a model like this, if anything, it looks worse. You know, again, the gray line bounces around, but the green and the blue and the light blue lines are even a little bit higher than the corresponding ones on the first approach. But basically the same conclusion that you would draw here, which is to say neither one of these are drawing from this posterior distribution very efficiently. They're going to have a lot of autocorrelation, even assuming the MCMC central limit theorem holds. It's going to have a very large standard error. So if you estimate a posterior mean or calculated a posterior predictive distribution and took the mean of that, you would have a large amount of uncertainty as to whether that mean that you calculate from a finite number of draws from a Markov chain is close to the true posterior expectation for this model if we were able to calculate it analytically, which we're not. So that's another way of saying that even if the Markov chain central limit theorem holds, the effective sample size would probably be very small, or at least small relative to the nominal sample size. And in order to counteract that, you would have to get, thousands or maybe millions of draws, each of which is highly dependent on the adjacent draws, in order to get reliable posterior means that have reasonably small standard errors. So this picture is kind of novel, but situations like these which were very common for about 1995 to 2010, when almost all the approaches to Bayes in inference were Gibbs samplers, or Gibbs sampler combined with Metropolis Hastings. And so people had to do millions of iterations and had to burn in for 500,000 iterations or something like that in order to be reasonably confident that the thing had converged and to have a high enough nominal sample size drawn from the posterior distribution to have an effective sample size of a couple hundred. And for a long time, that was just kind of the way it was. For non-trivial Gibbs samplers, it often just is that way. And sort of people kind of accepted the fact that to do Bayesian analysis, you'd have to do, a large number of iterations. And that problem got mitigated somewhat in the 2000s by the fact that computers got a lot faster and we got, multiple cores on a single computer, all kinds of things like that. But I think the more fundamental solution, and the solution that Stan tries to achieve, is to get draws that are not so dependent from one draw to the next, and to get effective sample size in the hundreds, even if you do like 2,000 iterations and throw away the first half or something. So you can actually do a multinomial Probit model in Stan. The homework didn't ask you to do it, and it moves around the posterior distribution a lot better than what you see here. Unfortunately, the posterior distribution can be multimodal, which causes other problems for Stan, but that's kind of a separate issue. And so I forgot that I did this actually, but you can look at the effective sample size of, each of these things, and you're getting numbers that are, double digits, triple digits, even though for each of these, I estimated 8 chains for 2,500 nominal iterations. And so the ratio of effective sample size to nominal sample size is pretty small here. You can also look at autocorrelation plots. These are for the intercepts, but it would look pretty much the same for any of the parameters. If you just look marginally, the correlation is still up above 0.5, out past 20 lags or something. So these are a measure of marginal association, whereas these plots that I prefer are a measure of multivariate dependence. But you would get the same conclusion either way. And you get the same conclusion from both approaches. So the second approach is in red here. You can also look at trace plots. So the fact that these snake around a good bit, sometimes high, sometimes low, is evidence of the chain not mixing well. What you want to see from these is a lot of movement basically on the same range, indicating that the mixing is well throughout the marginal or the distribution for that margin. So basically any measure of efficiency that you look at is going to show that these two Gibbs samplers are not very efficient ways of drawing from this posterior distribution, even though it's a perfectly valid posterior distribution to want to draw from. And so hopefully things like Stan will make it easier to estimate models like these. There's actually a third Gibbs sampler that has been proposed recently by these two guys, Burgett and Hahn, that overcomes some of the problems in the two Gibbs samplers that we saw here. But it's still a Gibbs sampler, and it still has the problem of the conditional variance can be a lot smaller than the marginal variance, so it takes a lot of iterations for it to mix well. But you can build upon these ideas in Burgett and Hahn to estimate a model in Stan that has pretty good performance. And so I think this is a concise illustration, or it would have been more compelling if I'd actually done the Stan code for this, but where Stan can get the dependence down to 0 at like 10 lags or so, and these other approaches are still having non-trivial amounts of dependence out to 400 lags or something like that. So any questions about the multinomial Probit one? No? Yes?
Why on page 8 and page 10, we've got for peer, it's always 1, it's constant 1. This is like empty, is it?
Yeah, because peer, I guess, is the reference category. So it's constrained to have an intercept at 0. Yeah. Don't worry about that one too much. So that wasn't actually estimated. That was fixed. And that's why it doesn't show up here. No. That's my bad. This is the variance, the estimated variance of the error correlation, estimated variance of the errors for the peer choice. And this parameter is fixed to 1 for identification reasons. And so it's constant, and thus it doesn't really have a well-defined autocorrelation. So that's why it appears blank there. In any event, all the other ones suggest that it's not going very well. Okay. Question 3 was about the student T problem. And so using the data set on political economy risk that we've done a couple of times before, And so I have stand code for each of these. But first I want to talk through some R code. Any event. Just to get a better handle on some of these transformations. So the first part of the problem asks you to put a gamma prior on the degrees of freedom for the t distribution. And so we can illustrate that in R by drawing from a gamma distribution that has an inverse scale of 1. So that'll be the new base variable. And then in order to make a transformation of that, we'll divide by an inverse scale of 0.1, which is equivalent to multiplying by a scale parameter of 10 to get our prior distribution for the degrees of freedom parameter nu. And so if we see this in terms of a plot, the green density here is the, which you can't even really see too well on this projector, is the prior density for new base. So a gamma distribution with a scale of 1. And so most of those numbers are going to be between 0 and 10, and all, even more so on the log scale, which is what Stan prefers in order to keep its leapfrogging approximations accurate. But the distribution for new is the black, or it's the same, it's overridden with the red line, is really spread out. So it has a mean of or a median of 20 or so, and a really long tail that stretches out past 150. And so if we put that gamma prior directly on new, Stan would have to be drawing from a posterior distribution that's influenced by the prior. They could easily go into triple digits. And so that it makes it more difficult for Stan to determine one step size that works really well when some parameters can be really big and other parameters can be really small. And so by specifying the primitive parameter new base as something with a scale of 1, and then scaling that up by either multiplying by 10 or dividing by 0.1, we get a transform parameter nu that can go into the likelihood function, but Stan really only has to care about the new base parameter, which has a more reasonable prior distribution from Stan's perspective, but implies exactly the same information about the degrees of freedom parameter through the transformation. And so that is illustrated in the Stan function by declaring a parameter with a lower bound 0 of new base, and then in the transform parameters block, declaring a parameter new, and then dividing new base by your inverse scale hyperparameter in order to get a distribution for new that you can then stick into the student t likelihood. So starting to get a little short on time, so I'll run through the rest of this kind of quickly. So these are the relevant lines of the Stan code to see how that would work. There's also a number of different ways to construct a double exponential distribution, and a double exponential distribution is pretty popular among Bayesians for a coefficient prior on coefficients. So it has this PDF, 1 over 2b times e to the negative absolute value of the coefficient divided by the scale parameter b. And its PDF has this form here with like a peak at the median, which in this case is going to be 0. So it has this shape that concentrates most of the density near 0, but has pretty long tails, and it's symmetric in both directions. And so Stan has the double exponential distribution, but the literal form of the PDF is subject to the same scaling considerations that we saw with the gamma distribution. And so one of the ways in which you can combat that, one of several, is to use an inverse CDF transformation. And so this is going to involve a double transformation. So in our code, we have a standard normal random variable z. We take the z and we put it into the standard normal CDF to get p, and this implies that p is going to be distributed standard uniform. Anytime you have a variable that's distributed according to one distribution and you put it into its own CDF, the resulting values are going to be distributed standard uniform. And then we can use the inverse CDF function for the double exponential distribution, which is probably easier to read here. It involves the sign of p minus 1/2 and the absolute value of p minus 1/2, etc. That construction will produce a transform parameter beta that has a double exponential distribution. And we can prove that to ourselves by going through all those transformations and then plotting the density again. And it has exactly the same shape that we saw before. And so we can take that beta and multiply it by x and go into the likelihood and whatnot. But from Stan's perspective, the parameter it's trying to draw from the posterior distribution of is z, which has a standard normal prior, which is Stan's preferred way of operating. So in a manner of speaking, we're reparameterizing the model such that we have the same prior information on a transformed parameter that we would if we just did a literal version of the model, but we are defining things in such a way to get computational advantages in the sense that it's easier for Stan to draw from a posterior distribution that's closer to normal than it is for Stan to draw from a distribution like this for a primitive parameter that is far from normal. It has long tails and it has the sharp peak and the absolute value and all that. So that's another way to construct draws from a or to construct a double exponential distribution. And the relevant lines of Stan code are given here, and there's a double exponential 1 file in the zip file for the homework that has the complete model for this. Another way in which you can construct a double exponential distribution is by subtracting two independent exponential distributions. That's where the double exponential distribution gets its name. So in R, if we just draw from an exponential distribution twice and then construct beta by subtracting those two, again, we get the same shape that we saw the previous two times, which is again something that's known. And so we could do a model like that in Stan where the relevant lines of code are just exponential b priors for x1 and x2, and then the difference of those in transform parameters to make beta, multiply beta by x, and have that go into the likelihood. This form actually does not do well in Stan because x1 and x2 are not individually identified in the sense that the distribution of x1 minus x2 is the same as the distribution of x2 minus x1. And so you get a multimodal posterior that is even more difficult to deal with than this distribution would be for Stan. So you can do that construction. It turns out to work terribly in the Stan code. Another approach along the same lines that actually suffers from the same problems is to use the fact that the exponential distribution, of which you're creating two of and then subtracting, has also a closed form CDF given by this expression here, negative log of 1 minus the probability divided by the scale factor. So you could do the same construction, take draws from a normal distribution, put them into the standard normal CDF to get draws from a uniform distribution, use the inverse CDF, that should say inverse CDF function for the exponential distribution to create x1 and x2, and then subtract x1 to x2 from x2 to get a distribution of beta that is again going to have this same shape here, but again is going to suffer from the same problems when you do it in Stan due to the multimodality of the distribution. Another approach is to do logarithm of ratios of standard uniforms. So we could do that in our code. We could do that in Stan code. We get a prior density that again looks like this, and we could do all that in Stan pretty easily. So there's 5 double exponential files in the homework answer key that explain how to do each of those approaches. I think in your homework it only asked you to compare the plain approach to one of those, but in the answer key I did a few comparisons, and so just the plain first version of the double exponential works pretty well. You get effective sample sizes for all of the parameters in the thousands, and if you did the dependence plot, it would look pretty good. The second approach that uses the inverse CDF method might be a little bit better on this criterion, but the other ones work pretty bad, and that can be seen from these ridiculous R hat values. So those are the things you want to be close to 1. Clearly they're not in this case. That's due to the multimodality of the distribution and Stan having a hard time dealing with that. So the last approach is a little bit better, but still not nearly as good as the first two. It has a dependence plot that looks like this, which is not so bad, but you nevertheless reject the null hypothesis that all the chains have converged to the same distribution. So the right answer to this question is basically the first approach that was specified in the homework is actually a better way of drawing from the this posterior distribution than, or it's as good as the second approach and better than all the other approaches in this particular case. But this does illustrate that there are different ways to imply the same prior information on a parameter, and different ways, logically equivalent, but computationally they can have very different effects on Stan's ability to draw from that posterior distribution efficiently. And so that was the main thing that I was trying to get across on the third question, is that, for the same model logically, you can have very good performance, you can have very bad performance. And for non-trivial models that you estimate with Stan, always have to be thinking about how can I make this easier for Stan computationally without changing my prior beliefs about the parameters. What can I do in terms of reparameterizations? And then similarly, but a little bit different, to get back to the first question on Tobit, what can I do to calculate constants in order to reduce the amount of derivatives that Stan has to keep track of through its auto differentiation mechanism, etc., in order to make my code run reasonably quickly, even if I have a lot of observations. And so both the reparameterizations and the calculating of constants can play into the speed in terms of wall time. It can also play into the numerical accuracy of the Hamiltonians. So all of that. All right, so we're essentially out of time. We'll have more opportunity to practice doing these transformations the rest of this week when we get into hierarchical modeling. Okay, so that is all for today. Cease broadcast.